Hi everyone. We are in Unit 4, which is about solutions. You could also think of them as homogeneous mixtures. And when a solute is dissolved in a solvent, the properties of that solvent can change. And there are certain properties that change based solely on the amount of solute particles dissolved, not on the actual identity of that solute. And in this video, we're going to talk about those properties which are called colligative properties, and also look at this Vant Hoff factor, which we're going to apply to electrolytes. Here is the definition of colligative properties. They are properties of a solvent that change based on the number of particles dissolved, not on the identity of the particle. This is interesting. So pretend that I have a solution. Let's say it's 20 milliliters of 0.24 moles of double-stranded DNA. And if your double-stranded DNA is about 20 base pairs, what would be the average molecular weight? Probably that's around 13,000 grams per mole. The way that this sample of DNA affects the water is the same way that 0.24 moles of, let's take the anti-cancer drug Taxol, and it has the molar mass or molecular weight of 854 grams per mole. So yeah, there's more grams in 0.24 moles of DNA than there are in 0.24 moles of Taxol. So there's literally more material, but there are an equal number of particles. That means these colligative properties that I'm about to tell you, they change the same way, whether it's DNA or Taxol, even though they have vastly different molar masses. Now, there are 4 colligative properties that we are going to learn about in this video, plus maybe 1 or 2 after this. 4 colligative properties. And I ask my students to memorize these phrases because it will also tell you how this property changes. For instance, I think the first one we're going to talk about in the next video is going to be freezing point depression. So that's something that I would want to memorize. Freezing point depression. Boiling point goes in the opposite direction. Boiling point elevation. I think the freezing point is easy to remember because when you want to melt the ice on your driveway, you salt it. You add a solute, and that lowers the freezing point so it's harder to freeze that water. So the ice melts when it's at 0 degrees Celsius outside. What about vapor pressure? Vapor pressure lowering. We won't use depression. We'll use lowering. Um, does that make sense? Remember that phrase that I talked about maybe a couple of videos ago? The higher the boiling point, the lower the vapor pressure of a solvent. So those things correlate well. The last one, the fourth one, is osmotic pressure. The osmotic pressure of a solvent will change when you dissolve stuff in it, and osmotic pressure increases. So we'll call this increasing as you dissolve more solute. Okay. I'm going to give you the equations, but I'm not going to dive deeply into what exactly each variable means. For instance, freezing point depression. The delta T of the freezing point, so the change in the freezing point, is equal to some value, it's called I, times the freezing point depression constant, and then M. Okay, let me explain what's going on here at least. So it's freezing point depression. So how much lower do you make the freezing point? That's your delta, and it should be a positive number. Okay, so um, don't be hung up with the the equation T final minus T initial. Okay, because this has to be positive. And same thing with the boiling point. The boiling point change is going to be positive. So you determine whether you want to add to the freezing point or melting point, or add to the boiling point. Add or subtract to the boiling point. That was horrible. I'm sorry. I messed that up. So if you have a delta T, you will take the normal freezing point and you will minus that delta, so you get a lower freezing point. If you have a delta TB, a change in boiling point, you're going to take the normal boiling point, like water's 100, and you're going to add that number so it becomes higher. Okay, and this has the analogous constant. This is a change, okay, and it's going to be positive. This I, that is what I'll explain for the rest of this video, this Vant Hoff factor. For many cases, for many problems that you'll do, it's just going to be 1. So it doesn't affect anything. Again, this is it doesn't really have a fancy name. It's just the freezing point depression constant. Uh-oh. Come on, ink. Depression. Oh, that worked. Okay. And then M. M, you got to be careful. That is molality. Okay. And that equals moles of solute divided by kilograms of, not of the solution, kilograms of just the solvent. We had a video where we talked about different ways to express concentration. It's very important that you know what the denominator is. Is it kilograms of the solvent or is it kilograms of the solution? This is just of the solvent. Okay, so great. If you know, and you'll look up or you'll be told the KF, and you can figure out the molality, then you know how many degrees lower you have to make the normal freezing point. So you'll be given, most likely, the freezing point of the solvent, whether it's water at 0 degrees or some other solvent. Okay, this I. When the molecule that you are dissolving, you know does not ionize, then that is 1. So let me give you some examples. I equals 1 for molecular compounds or covalent compounds. Molecular or covalent compounds. Maybe it's easier just to say not a salt. Not salts. Things that have ionic and cationic components. So, for example, some classic examples. I don't know, DNA, you could treat as a particle that doesn't break up when you put it into water, when it dissolves in water. A much smaller example, glucose. Okay, that's a very popular example. You dissolve glucose in water. If you dissolve 0.24 moles of glucose, you have 0.24 moles of particles. That's what it literally means. Let's do like naphthalene. Naphthalene is mothballs. So what you're thinking here is that the um, if the molality of glucose is 0. Let's see, 2. I keep using 2.4. Let's say 2.9 molal. So just be careful. That's again molal. Then the particle concentration is also 0.29 molal, because we're going to multiply that these terms by 1. So they're equal. Basically, they do not break up when dissolved. So they dissolve, use 1 when the solute, when they dissolve but not break up into smaller components. But not break up into. I'm making this. I'm so sorry. I feel like I'm making this more complicated than it needs to be. Into smaller components like ions. Okay. Let me give an example where the Van Hoff factor is not 1. Maybe that's the better way to go. So for instance, um, when I does not equal to 1. Okay. So for instance, if I say I dissolve um, 2.3 moles, I keep using 2 again, 2.3 moles of sodium chloride. Well, we know that sodium chloride will break up into its ions. This is fully soluble. So that is, we get actually 4.6 moles of particles. So that's the number actually you'll be imagining that you have in the solution. So, like, where does this math come from? So if you have I, Kf, and M, if you know your M, and let me pick a different number. If you have an M that is 1.7 molal NaCl, your I is going to be 2, because you know that NaCl, when dissolved, becomes Na plus aqueous plus Cl minus aqueous. So that's where you get the 2 from, and that is the Van Hoff factor. So yeah, your effective molality is not actually 1.7, it's 1.7 times 2. This is unitless. So you really have like a 3.4 molal solution of particles. A solution of particles, not a solution of sodium chloride. So that's I equals 2. Now this 2 is, they call it calculated, because it's just coming from the idea that this dissociates 100%. So this is calculated. But really you're just counting the ions. Count the ions, 2. 2 ions per compound. So we are using this mainly when we know we get ions. And let me make that abundantly clear. You will use I if solute is an ionic compound that dissociates, that breaks up into its ions. Now there's a special name for this. These ionic compounds, they're called electrolytes. And if it's dissociates 100%, it's a strong electrolyte. So if dissociate 100%, that equals a strong electrolyte. You've heard of sports drinks that have added electrolytes? Well, because when you perspire, you release a lot of salts, and you need to replenish those salts. So, a drink like Gatorade or Powerade or some other high electrolyte drink that has a lot of salts in it, you would want to take to replace the salts that you did lose. The other thing is that when you have a solution of water that has strong electrolytes, then that solution can conduct electricity. So you have, for instance, Na plus, Cl minus, just floating around. So charge can travel through that water. So the solution can conduct electricity. Okay. There's one more thing about this Van Hoff factor. Again, normally you'll just count up the number of ions per molecule. So let me give you one more example, and then let me show you something kind of interesting. For instance, if we have, what's something that we know that dissociates? 7.31 molal of Li2 carbonate. You see how you also have to kind of memorize the solubility rules? Because you want to know whether something's soluble. When we learn solubility rules, it technically means it breaks up into its ionic parts. So when we plug it into the formula, you have delta T, and we'll stick with freezing point. Delta TF equals I, the KF, and then this molality, 7.31. But then this number, I, you should plug in 3. Okay? Because Li2CO3 solid breaks up into 2 Li plus aqueous plus CO3 2 minus aqueous. That's where I get the 3 particles. Okay? Okay. We'll do some real examples in the next video when we talk more specifically about freezing point depression. But see, that's I is showing up in both of these equations. I actually never gave you the equation for vapor pressure or osmotic pressure. We'll do that later, okay, after we've talked in a different video more carefully about these two. But vapor pressure also has that I term. No, actually it doesn't. Osmotic pressure has this I term, the Van Hoff factor. Finally, it's not as easy as actually counting the number of ions per molecule of the salt. Like I said before, this is calculated, just literally counting. But there's experimental as well. You tell me the trend that you see when we look at calculated Van Hoff and measured Van Hoff. This is from the Adam's First Textbook by Burge and Overby. Sucrose. Remember how I said glucose? You treat it as one molecule, one particle. So the calculated is 1, and when they measure it, it is literally 1. So they could back calculate to figure out what is the actual Van Hoff factor. So this measured one, you could call it the Van Hoff factor, but sometimes the textbook will call it the effective particle number. Like what does it truly do in solution? How does it truly act? Because look at sodium chloride. We calculated as 2 because you get 1 sodium and 1 chloride, 1 Na plus and 1 Cl minus. But see, the actual is lower. It's a little lower. And actually, this is what you would use if you're given it. If you're not given the effective particle number or the true Van Hoff factor, then just go with the counting. You count the number of ions per molecule. But if you are given it, then you use this as I. use that as I. Why is that the case? It tells me that there is a small percentage of sodium chloride that sticks together, that stays as a pair, technically an ion pair. So I don't know what that percentage is. It's zero point 0.1, right? What is that? Yikes. Not 20%, but messing that up. Well, I could figure it out. 0.1 divided by 2. 0.05, and then times 100. 5% of the sodium chloride stays as an ion pair. 95% break up into its two ions. I think that's how the math works. Don't quote me on it, but a little bit stays as an ion pair. So there are some ionic salts that like to stay as a pair. Look at this iron 2, no, iron 1 chloride. Iron 1 chloride. You expect 4 ions. Fe plus? Man, Fe, did I say Fe2? Fe3 plus, because you need 3 Cl minuses. Yeah, 'cause I gotta review um, my compound, ionic compounds. But there are 4 particles here. But in actuality, it acts as if there's only 3.4 particles per molecule. Okay, I believe that's all I want to say. Again, if you're not given I, in the vast majority of cases, right, you're not going to be dissolving a salt anyway. So just don't even put I in the equation because it's just one. Um, but if you notice that they do dissolve a salt, then you just have to be cognizant that that one molecule of salt will break up into several particles, and that's what you're going to be using to calculate the colligative property because it's based on the number of particles. Number of particles. If you know it's a salt and they don't give you the real I or the effective I, then just use the calculated. I've actually seen problems, it's kind of neat, where they measure the delta T, they know the KF, and they know the molality. And they want you to calculate what the true I is, because it's probably not an integer, it's probably some decimal. In the next video, I will tackle some examples of freezing point depression and boiling point elevation. And yes, we will actually start plugging in numbers and calculating the change in the freezing point and boiling point.